So, let us now speak about the Lagrange multiplier rule. The Lagrange multiplier rule is associated with something we call constraint optimization problems. In the last class that we had, or the last lecture that I have given, in there we had been seeking x and y which minimize or maximize a function x y over whole of R2. We were not putting any restrictions on x and y, but now we can put a restriction on x and y, and we seek to minimize a function of two variables. You can maximize also, do not worry, subject to g x y is another function of two variables. So, basically what we are trying to say that only those x y. So, if you form a set, so we call it C. So, this is called the feasible set. So, take only those x y in R2 which satisfies how would you go ahead and solve this? The key idea of solving this is the following, and that is quite natural. Suppose by a stroke of luck the function g x y is such that y can be written as some function psi of x, right. Then you can immediately do one immediate thing, that you can now put back, instead of in f you can now put back, instead of y you can put psi of x. Now, your original problem now becomes to minimize this over only x, and now it becomes an unconstant optimization problem which you can minimize. Now, so what we are now going to do, we are now going to just first compute a point x bar which satisfies this, and check whether by using the second order standard second order condition whether this x bar is a minimizer of this function. Now, once you have done that, you can obviously you can plug in the value of x bar here, and obviously you know y is psi x bar. So, my y bar is psi x bar, and so this x bar and psi x bar are actually the solution of the problem. So, x bar and y bar is psi x bar is the solution of the problem. If this happens, it will be pretty nice. For example, if you say okay, say I want to find a point on the plane, on the line, say I take the straight line. So, I am giving an example where such a thing can be done, but it might not be the case that you can always do it. So, what has been the step? Our step has been eliminate and then differentiate. So, now for example, I am asking that find a point on this plane Ax plus By equal to C such that the distance from the origin of that point is minimum. That is, you find a point, basically from the origin you are dropping a perpendicular on this plane geometrically. So, this is your origin and you are trying to find this point x bar y bar. So, you are from a point of view of perspective of a minimization problem, I can set up the problem of minimizing x square plus y square, that is the distance of any point from the origin, subject to, for this straight line, Ax plus By minus C is equal to 0. Here, suppose I take A equal to 1, B equal to 1 and C equal to 1. So, suppose I take A is equal to 1, B is equal to 1 and C is equal to 1, basically x plus y equal to 1, that is that line which passes through 1 0 and 0 1, thing which you know very well. Now, so my problem becomes minimize f of x y subject to x plus y minus 1 is equal to 0. Now, what is y? So, from here it implies that y is equal to 1 minus x, where f of x square or f of x y is x square plus y square. So, basically now my original problem in the form of this is my psi of x. So, f x psi of x now becomes x square plus 1 minus x whole square. So, this is equal to x square plus 1 minus 2 x plus x square, that is 2 x square minus 2 x plus 1. Basically now I have a single function of one real variable. Here I wrote differentiation, basically you have to find df dx of this, which is 4 x minus 2, and find. So, put this equal to 0 and find x is equal to half. So, once you find x equal to half, you try out on this function again, you take a second derivative of this, that is 4, which is always strictly greater than 0. So, this would imply that x is equal to half is a true minimizer of this problem, and so what is y? Y is 1 minus x, so y is equal to half. So, x bar equal to half and y bar equal to half are the solutions of this problem, which is quite obvious from even the geometry. But this is not the only kind of problem that you are facing. Suppose you are unable to eliminate in a proper way, or if you eliminate, thing can be slightly problematic, because for example, if you have a problem of this form, minimize 3x plus 4y subject to x square plus y square minus 1 is equal to 0. That is, find the minimum value of the function 3x plus 4y when x and y are lying on the unit circle. Now, you can say, okay, why can't I eliminate? I can write y is equal to root over 1 minus x square, but no, you cannot write y actually as a function of x. You have to write y as a plus minus root over 1 minus x square. So, it is not a function, and in such a case you have no choice to eliminate and then differentiate. So, Lagrange taught us a very effective thing. Lagrange said, do not worry, there is a different way, you first differentiate and then eliminate. So, he constructed what is called the Lagrangian function. And this Lagrangian function you write as Lx y lambda, which is essentially defined like this, f of x y. So, you have a problem like this. So, this is the abstract version of the problem, and here is a concrete example which I have written on the left. Sub 2 means subject to. So, f x y plus lambda g x y, where lambda is some element in real line. So, now this L x lambda is a function of two variables. What he says is that first you, if x bar is a solution, then what I should do to find the solution, what should I do? The first step would be to differentiate. So, it is L x y lambda x, and then differentiate that Lagrangian function with respect to lambda, and that will only give you g x y, and that equate it to 0. Basically, it is telling that you have to first do the following: find those. So, here you have L x y lambda, and also, so you first construct this Lagrangian function, differentiate, and now when you have this, you now try to eliminate out lambda and get the value of x and y. That is the key idea. So, lambda here is called the Lagrangian multiplier. So, this is essentially a necessary condition. What if you think that this is a trick by which you can, if you just solve this and get an x y, you get a minimizer, your answer is no. It is essentially a necessary condition. It says that if x bar y bar, this is a thing which is not taught in your calculus classes in general, but let me tell you the real fact. If x bar y bar is a minimizer and the gradient of g at x bar y bar is a non-zero vector, then both the components of the gradient del f del x or del f del y, del g del x del g del y both cannot be 0 at the same time. Then there exists a lambda in R, a real number, such that L x y lambda is equal to 0. That is L x bar y bar lambda, this is 0. That is what Lagrange multiplier rule says, that is exactly what it is. So, you really have to know this condition, that if this condition holds and if x bar y bar is a minimizer, this will happen. See, in order to find a minimizer, I can actually start doing this, but the issue is that if I find a point that is only a point which is called a Lagrange critical point, it does not at all tell you that that is a minimizer. The most books will write that as a minimizer, there are a lot of hidden things which they do not tell you, and for that you really had to go and study a branch of mathematics called optimization theory, but we do not do this here. We now really take an example, the concrete example that we had taken, we now try to do it step by step. So, minimize 3x plus 4y subject to so this is my fxy and this is my gxy. So, I construct the Lagrangian function fxy plus lambda gxy is equal to 3x plus 4y plus lambda x square plus y square minus 1. Now, what is the meaning of so let us write down the gradient vector. So, take the del f del x with respect to x. So, it will become 3 plus 2 lambda x, that even if you write minus does not matter much in this particular case, but does not matter, we will just take the convention we are using. So, 3 here you have 3 as derivative, here you have 2x. So, that is all. This is the gradient with del f del x, basically del L del x, and then with respect to y it will be 4 plus 2 lambda y, and this vector is actually the 0 0 vector, 0 vector. Right. When I am writing this essentially means this. So, which means that 3 plus 2 lambda x is equal to 0, which means 4 plus 2 lambda y is equal to 0. Okay. So, what does this mean? Can we eliminate lambda and do something? From here we can have x is equal to, what do we have? X is equal to minus 3 by 2 lambda and y is equal to minus 4 by 2 lambda. Now, I have to get rid of this lambda and get something. So, but I know that this, if this is my x bar and y bar, right, I have solved this and this is my required x bar and y bar, but this lambda is something undetermined. So, what I do, I go to the fact, I use the fact that g x bar y bar is equal to 0. So, if this was a truly a minimizer, then it should satisfy this basic constraint. So, I will have x bar whole square plus y bar whole square is equal to 1, which will give me minus 3 by 2 lambda whole square plus minus 4 by 2 lambda whole square is equal to 1. So, it is giving me basically same as writing 3 by 2 lambda whole square plus 2 by lambda whole square is equal to 1. From here we can really figure out lambda. So, what do we get from, if I calculate this out further, let me calculate it out here. So, we remain on the same page of the problem. So, if I calculate this out further, it will be 9 by 4 lambda square plus 4 by lambda square would be equal to 1. So, that means 1 by lambda square 9 by 4 plus 4 is equal to 1. So, it is basically becoming 1 by lambda square 25 by 4 is equal to 1, or lambda is equal to plus minus 25 by 4 square root. So, lambda is equal to 5 by 2 plus minus. Now, you have two values now. So, what are you going to do? So, now you will get two sets of x bar and y bar. So, here x bar, first take lambda equal to 5 by 2. So, in that case your x bar would be equal to, what would be x bar? X bar would be equal to lambda I am putting 5 by 2, it will become plus minus 3 by, so here first if I put lambda equal to 5 by 2, it will become minus 3 by 5, and y bar would become minus 4 by 5. Similarly, x bar, if I put this as minus, would become 3 by 5 and y bar would become 4 by 5. Now, the question is, which one gives me the maximum, which one gives me the minimum? Do they at all give me maximum or minimum? How do I know? See, this is a question which is never answered to you in the calculus class. The interesting fact is that whether such a problem would actually have a maximizer and minimizer. If you look at the set, the feasible region here, this is x square plus y square equal to 1, and this is a closed set and a bounded set. It is essentially what is called a compact set in 2 dimensions. We have not discussed all this. So, I am telling you where you are not told, and you are just told, okay, now somehow you put x bar and y bar into the top one, the objective function, you put both the sets of value, whichever is the lower one, you take that as the minimum value. But how do you guarantee that a minimum would be there? So, if because this function is a continuous function, there is a minimizer and a maximizer over a compact set, that is a result in 2 dimensions which we have not spoken about. Now, that is a very, very important result when you have on this sort of closed bounded set. So, this problem has a minimizer and a maximizer, and both of them should be at least as one minimizer and one maximizer, which are global maximum, minimizer and maximizer, and you will immediately know that here at least. So, which means they should give me a maximum value and a minimum value, right. And so, and both of these maximizers and minimizers must be actually satisfying some sort of this Lagrange multiplier rule. This is also something you have to keep in mind. So, what you have to now do, once you are guaranteed the maximizer and minimizer exists, now you plug in the values and you figure out which is the maximizer and which is the minimizer. You put in the minus values, you will get a minus something. If you put in the plus values, you will get plus something. So, this is the minimizer. This is the minimizer, this is this one. So, you see how nicely we have been able to at least get a point where we can speak about whether it is a maximizer or minimizer or not. But in this case, if you really want to determine or guarantee that this is a minimizer or maximizer, you need to use second order condition, but that is beyond the scope of this course. Here, by arguing the way I have just argued, people can say whether we can choose from the Lagrangian, the critical points that you get, the point that satisfies the Lagrange multiplier rule, that which is the minimizer or which is the maximizer. So, with this very brief idea about the Lagrangian multiplier rule, I end the course here. Please look at the examples in your assignments, and in the last week we will just have 2 topics which we will break it up into 3 and 3 classes. One is multiple integrals and another is infinite series, and both are important in understanding calculus. Thank you very much.